Alright, so second video on eigenvectors and eigenvalues. This time we're going to be finding eigenvalues. Now in the previous video we said that we defined eigenvectors and eigenvalues. We said that a matrix times the eigenvector will be equal to lambda times the eigenvector. And lambda is an eigenvalue. Okay. Remember that though is just a number. It's just like a scalar. The number 3, the number 5, the number 7. You could use x, y, z, but for eigenvalues we use lambda. Alright, so I'm just going to work on that equation a little bit more because it's not as useful as it could be. I'm going to set everything equal to 0. So I'm just going to rearrange it to say that a, v, minus lambda v equals 0. Alright, pretty useful at the moment. Now, I can probably move this vector because it's you can see we've got a common value here. So I can move my vector on the outside and I can make that a minus lambda is equal to 0. That's getting better, but you've got a matrix, subtract a scalar. But we don't really deal that way. You can't do a matrix minus a scalar unless you had an identity matrix to go with the scalar. So we can set that up, a minus lambda times the identity matrix, v. Alright, that's going to be really, really useful for us to find our eigenvalues. Alright, so now that we know all of that stuff, we can jump into an example. We're going to go a little bit further with that, but not until we've gotten a little bit into this example. Now, if A equals 1, 6, 2, 2, find the eigenvalues associated with the matrix. Eigenvalues might see more than one here. Now, we're going to use this portion here. We're going to find out what this is. So A is 1, 6, 2, 2. 1, 6, 2. Wrong way. And now I'm going to subtract the identity matrix of lambda. So lambda is just a number like 5, 7, 9. So the identity matrix of lambda is lambda 0, 0, lambda. Now if I subtract one from the other here, I get 1 minus lambda, 6 minus 0, which is 6, 2 minus 0, which is 2, and 2 minus lambda. Alright, so now I've got a matrix that is A minus the identity matrix of lambda. But now take a look at what we've got here. If we look over here, this times this is equal to 0. So that must mean that either that's equal to 0, which is our eigenvector, or this is equal to 0. So this times this equals 0. So if that's equal to 0, that means the determinant of that must be equal to 0. So the determinant of that is going to be 1 minus lambda times 2 minus lambda minus 6 times 2. Alright, so there's our determinant. Now our determinant's going to be equal to 0. Now you can expand that, and what you're going to end up with is negative 12 out the front there. 1 times 2 is 2. You're going to end up with negative 2 lambda, negative 1 lambda, so negative 3 lambda, and lambda squared. So tidying that up a little bit, you'll end up with a quadratic lambda squared minus 3 lambda minus 12 plus 2 minus 10 equals 0. Now that you've got that, you can just solve it, so it'll factorize quite neatly. into lambda minus 5 lambda plus 2. And so that means that our lambda values, lambda equals 5 or negative 2. All right. So if we go back to our definition and think about what's really happening here, what we've got is a matrix 1, 2, 6, 2. If I multiply it by the eigenvector, so some unknown vector, it will be equal to either 5 or 2 times that same unknown vector. Alright, so we just need to find out now what that unknown vector is. That's going to be our eigenvector. We'll do that one in the next video.